introduction. And yes, as Aju said, I have been a postdoc in Sydney over 4 years, and yes, I benefit a lot from such an experience. And yes, my main research field is chiral physics, but as Aju said, now I'm moved a part of my interest to the dark matter field, and actually I'm a beginner in this field, and but I find it is very interesting research field. So today I will talk about the direct detections of SUSY WIMP and cosmic ray upscattered dark matter, and this talk is based on our following works. Um, actually, in the end, if I have time, I may introduce our recent work about the KeV gravitational dark matter for the Hubble tension. And this project is still ongoing, and I only have some very preliminary results to show. And now, okay, let's start my talk. And the first part is about the status of SUSY neutralino dark matter. I think most of us are very familiar with this topic. Um, I will uh, I will quickly overview the constant status, mainly focus on the minimal framework, and then I will move to the sub-GeV dark matter direct detections, and talk about one possibility that is the dark matter, the sub-GeV dark matter was accelerated by the cosmic ray. And in the end, I will talk about the gravitational dark matter for the Hubble tension. So let's start my talk. And as we know, we have many evidence for the existence of dark matter, and dark matter account for the 24% matters in the universe, and it is very important, and but remain elusive uh, in our uh, in our field. So as we know, there are normally we have two production mechanism of dark matter. One is the thermal production, thermal production. That means we have the dark matter as in the early at the early universe, and it is the thermal equivalent with other particles, and then when the universe expands, it freezes out and gives the correct radiation density. The other way is non-thermal productions. That means the dark matter does not exist at the early universe, and it comes from the the decay of heavy particles, and then finally reaches the required radiation densities. And as we know, the WIMP is a very beautiful candidate to explain the dark matter evidence, and it's based on the thermal production pictures. It is freeze out, and when the universe expands, and then we give the correct radiation densities with mass around 100 GeV and weak couplings. So it seems a very natural picture of the dark matter, um, but uh, but we did a lot of searches of WIMP, but we unfortunately we didn't see it. And this is a very short history of the WIMP dark matter. So because we have no information about the dark matter mass, the spin, and other properties, we only know it interact gravitationally, and uh, uh, the so we we hope the dark matter can interact with the other small particles. And according to the calculations in 1970s, uh, Weinberg and Lee and give the lower bound of WIMP dark matter mass. It should be it cannot be less than 2 GeV. So this bound is very famous and still works now. And in 1990s, someone studies the upper bound. If we know the upper bound, we can know which machine we need to discover the dark matter, just like the just like collider searches for new particles. If we know the scale of new particles, so we know how much energies do we need to we need to discover the new particles. So the unitarity limits on the dark matter on the WIMP mass is around 700 TeV, and recently I think someone argued it can be heavier when we consider more complicated calculations. So roughly now we know the WIMP should lies in the mass range between 2 GeV and 300 TeV. So it is a very large mass range. And so in this picture, it has been showed many times, I think, in other guys' talk. So we can see the dark matter can have very broad mass range. This is the WIMP. This is a WIMP that has been discussed heavily, and there are also other candidates. For example, the axino, gravitino, and also the fuzzy dark matter, axion. And for the heavy one, we have the WIMPzilla dark matter. So the interaction or the cross sections of dark matter, it can range from 10 to minus 39 to 10 to 40. So this is a very broad range, and this leads to the difficulty in discovering the dark matter. WIMP. Now I will firstly talk about the SUSY WIMP dark matters. I mainly focus on the neutralino dark matters. Besides neutralino dark matters, we can also have neutrino dark matters or other candidates. But neutralino dark matter seems a very natural candidate in supersymmetry. So as we know, supersymmetry is a symmetry between the bosons and fermions, and which was firstly introduced in 1973 as part of the extension of the special relativity. And the supersymmetry attract a lot of attentions because supersymmetry, it is not just a technique solution to some problems. For example, the hierarchy problem, the guard problem, or any other problems. It is a very beautiful framework to unify our fundamental forces. So in this sense, as such by Witten, SUSY is a part of a large vision of physics. So that's why many people like these models. So in supersymmetry, if the R part is conserved, we will have the lightest neutralino as the dark matter candidate. And if we wanted to search for the neutralino dark matter, so at first, I think we need to know the mass range of this dark matter. So this guy, the Goldberg, in 1973, he calculates the lower limits of the photino mass. Photino is interaction eigenstates of the neutralino, one of the lattice neutralino. So He got the bonds under some other assumptions. It is around 1.8 GeV, and for the dark matter photino mass. So up to now, I haven't seen some guys calculate the upper bounds, the results for the upper bounds of the photino mass, but it should be there and the same or more or less the same as the unitarity bounds for generic fermionic dark matter mass. So this is the details of the neutralino dark matter sector, and we have the neutralino sector in MSM. And then if we, these mass matrix can be diagonalized by the unitarity, 4x4 unitarity matrix. And the lightest one can be the dark matter, and it is a mixture of the four interaction eigenstate, spino, wino, and hexenos. So according to the component, the the lightest neutralino can be bino-like or wino-like or hexeno-like, or the mixture. So in this plot, it is the results for the relative density for several kinds of neutralino dark matters. So we can see that if the dark matter, neutralino dark matter is very hexeno-like, in order to give the correct the relative density, its mass should be around 1 TeV, 1.5 TeV, or something like that. And if it is a wino-like, and the mass should be around 2 TeV or 3 TeV, which depends on whether you include the other high order corrections or the Sommerfeld enhancement effects or something like corrections. And so but for very Bino-like dark matters, we can see the relative density is always higher than the observed values. It will overclose the universe, and this number corresponding to the other particles mass. There is we assume a common mass for other particles, and this is 3 times 5 times. This is 3 times of neutralino dark matter mass. And this is 5 times of the dark matter mass. So we can see in that case, if the other particles are heavier than the dark matter mass, normally it will overclose the universe. And but there are some several ways to get reduce the relative density. And one, for example, one is co-annihilations. The LSP can co-annihilate with star and the stop or wino or gluino other particles, or we can through the resident effects, the two dark matter annihilate through Z boson or Higgs boson or other Higgs bosons, or we can have a mixed states and the dark matter have the lightest dark matter, the lightest neutralino have the other components such as hexeno components or wino components, and then the interactions between the between them will be enhanced. Then we reduce the radix. So this is results for the constant direct detections for the neutralino dark matters. I think the gambit group should be have updated ones, or the I'm sorry for that. I didn't check their results. I think in my mind they should have new results. This is a result for the 2017. So from this plot we can see that the constant limits excluded most of all the part of the parameter space for the neutralino dark matters, and the gray shade shallow range are the allowed parameter space for the neutralino dark matters. So, but we have to see that even the exclusion limit is approaching the neutrino flow and they exclude a part of this range, the parameter space, but there are still some parameter space alive and even below the neutrino flow. So it is very meaningful to explore what happens for those range and also how to discover the dark matter below the neutrino flows, uh, because this range is within the RHC reach. So maybe the RHC can play an important role to discover the dark matter in this range. So I won't talk too much about this topic, and maybe there are other references, papers to discuss it. So there is one. So the question is, how can we escape the direct detection bounds on the neutralino dark matter in supersymmetry? I think there. This is from my experience. I think there are several ways. One is the co-annihilations, because in co-annihilations, the process contributing to the annihilation and will be different from that from scattering processes. So we can break up the strong relations between the radical density and direct detections. So that may help us to escape the direct detection bound. There's also another way we call it is called the blind spots. Blind spot it is it happens in some accidental case because if we to calculate the direct scattering the scattering cross section between dark matter and the nucleus, we can find that the couplings between the dark matter and the Higgs mediator or that mediator depend on this factor. And in this factor, if the relative sign between the Gigino 1 and the Higgsino is minus, we may tune its values to cancellate with the sine 2 beta, and then we can make this coupling vanishing, and then the cross sections, the scattering cross sections will be suppressed. So we have the blind spot. So this is called the blind spot. But the problem of blind spot is we lack of dynamical symmetry to realize this scenario. And I remember Carlos Wagner have tried to find the dynamical symmetry for the blind spots in the NMSM. But in the MSM, I'm not sure whether we can have a dynamical source for this special region. This is about the blind spots method. We also can have two ways to escape the direct detections in the very light dark matter limit. So this limit is also called dark Higgs. That means the dark matter, the neutralino dark matter are very light and annihilate through some light Higgs. and then it can below the constant limit, below the threshold of the constant direct detections. So then such a light dark matter can escape the constant direct detection limit. In MSM, I think the only feasible way is to is in the uh, alignment limit. Alignment limits in alignment. I will talk more about the alignment limit. In alignment limit, um, the only one Higgs is responsible for the electroweak symmetry breaking and coupled with the gauge bosons. The other one has no coupling with the gauge bosons and only interacting with fermions. And in that case, we can choose uh, the heavier CP even Higgs as a standard model Higgs. The other one, the lighter one, can be much lighter than the standard model Higgs boson. And this light Higgs can play the role of the mediators of the dark matter annihilations. So in this plot, we show the survival, the parameter space for the alignment limit without decoupling in MSSM. And you can see it is a very, very narrow range. It is a very, very narrow range. Uh, it requires a very low value of 10 beta and a very large Higgsino mass. Um, the very large Higgsino mass is required by the Higgs mass because if you want to get the alignment limits, we need a very large loop corrections uh, to the loop corrections to calculate the tree level contributions when we calculate the Higgs mass. So that will lead to the naturalness problems, but here we forgot about naturalness problems. We just to see whether we can realize a very light Higgs in the MSSM. So this green range is the loved parameter space for the very light dark matter, very light Higgs boson. So this mass uh, the yellow range is excluded by the R2C searches for the heavier dark matter, and this green range is physical ranges. So if we want to get this range, the time beta should be very small, and this plot is based on our scan in 2017. But as we know, the R2C collected more data on the Higgs coupling measurements and other measurements. So I'm not very sure whether this range can still exist in light of the current data. But it is a very interesting range because in this range we can have a very light Higgs boson, and it can be tens GeV or even less, and also very light Higgs bosons. Although we can have a very light dark matter, neutralino dark matter. So this is our results for the light dark matter in the MSM. So we can see those ranges can escape the most of the search at that time. But I think with the latest CDEX results or other direct detection limits, most of this parameter space, these samples can be excluded, or only a very narrow parameter space left. But this is the result for the indirect detections, but we can see it is far below the SMV or the dwarf constraints. Um, so we expect such a light dark matter scenario in MSM will be quickly covered by the direct detections. Oops. Oops. So this is for so this is the part of the very light dark matter in the supersymmetry, and then we move to another mass range. It is in the weak skew mass range, but from the 30 GeV to the 100 GeV for the dark matter, and we consider the light Bino Higgsino Bino and Higgsino scenario, and the motivation is like this. The light Higgsino is welcomed by the naturalists. So, but we know the Higgsino dark matter will have very strong interactions, and then the relic is much smaller than the observed ones. Uh, so the observed value. So whether we can have a light Higgsino to keep the naturalness and also realize produce a right radical density is what we want to answer, is a question what we want to answer. The light Bino, so we mixed the Higgsino with Bino component, and then we examine the parameter space, the feasible parameter space for this scenario. We can see that in this mass range, the direct detection are very strong. Limits are very strong and excluded most of them. But for the spin independent case, we can see there are some samples are much below the samples have the scattering cross section are much below the limits given by the xenon or even the constant xenon results or even the future xenon results. Um, this range happens in the blind spots. So in those range, we can realize the blind spots by tuning the parameters to get vanishing couplings between the dark matter and the Higgs mediators. But on the other hand, if we look at the spin dependent results, we can see this cancellation will disappear, and the projected Xenon 1T experiments will have the ability to cover the whole mass range. So that means in near future, the Xenon 1T will give a decision on whether we can have such a light Bino Higgsino dark matter, neutralino dark matter case. So this is for the medial mass range. Then we also moved to the higher mass range. It is we focus on the 1 TeV to the 3 TeV even higher. So we can see that this light blue is for the Higgsino dark matter, pure Higgsino dark matter, and this blue is for the Vino dark matter, and the gray point are the mixed states. So we examined 4 cases. It is a decoupled case scenario. That means we only keep the dark matter neutralino sector, and other particles are decoupled. Also the A final range, and we see that the Lux Zeppelin experiments will be able to exclude the Higgsino case dark matter and give a very strong constraints on the Vino dark matters. So according to all this, in the lower panel, we also studied the indirect constraints, but it's much weaker than the direct detections. So from these 3 scenarios, in these three scenarios, we look at the very light GeV scale dark matter and the 100 GeV dark matter, neutralino dark matter, and also the TeV scale dark matter. And the conclusion is very obvious. The loud parameter space is shrinking, and the near future or the future dark matter, direct detection dark matter experiments have the ability to cover most of them or exclude them. Um, Discover them or exclude them. So from my opinion, the minimal, the neutralino dark matter in the minimal framework is very very challenging. And so this motivate me to consider about other options. So one possible way is we goes to the light dark matter, more like light dark matter ranges much lower than the WIMP lower mass, WIMP lower mass. For example, the sub-GeV, sub-MIME, or sub-KeV, or even the fuzz dark matters. The other way is to go to the higher mass range to study the WIMP because for the we know the lower the light dark matter usually have the very good motivations and have plenty of candidates. So I choose to go this side, not rather than this one. So the first sub-GeV dark matter that we studied is the cosmic ray upscattered dark matter. It's usually called the CRDM. And this scenario is very interesting. And so as we know, the normally the usually the direct detections was limited by the threshold energy when the dark matter scattering with the nucleus. So this is the typical value for the nucleus recoils is about 20 keV. But from the recoil energy, from the recoiling energy equation, we can see that if the dark matter much less than the nucleus mass, we will have very small recoil energy and will not produce the observable signal in the normal WIMP direct detection experiments. So one way is one way to solve this difficulty is that if the dark matter was boosted by something or become energetic, then it will have much higher kinetic energy, and then it will trigger the direct detections. Then we can observe the signals. So one possible way is that the dark matter was heated by the high energy cosmic ray, and then the dark matter will become the energetic and boosted, and it may fly through the atmosphere and also pass through the Earth, and then finally reach the direct detections. So normally for this cosmic ray upscattered dark matter, we have two steps. One is acceleration by the cosmic ray. The other is attenuation effects by the Earth and atmosphere. So, oops. So let's see the element abundance of the cosmic ray. This is normal. This is results for the element abundance of the cosmic ray. We normalized to the hydrogen, and we can see that the helium-4 is the second dominant component. So in our study, we will focus on the cosmic ray that consists of the helium-4 and proton. And this result is the number, the density of the uh, cosmic ray. We can see it is dominated by the proton and then followed by the helium. So you can see their energy follows drops like the Power law, and but we can see for the cosmic ray can reach very high energies, and and some of them can much higher than the LGC energies, and for most of them will be around 100 GeV range. So such energy will be enough for us to accelerate our light dark matter. Oops. So when we calculate, when we start in the study of the cosmic ray upscattered sub-GeV dark matters, usually we have usually there are 3 steps to do. So the first step is we should calculate the elastic scattering between the CR and the dark matter. Here we focus on the elastic scatterings. We won't. We have another work ongoing is to discuss about inelastic. It is much more complicated than the elastic scattering. So this the first we need to calculate in differential volume the scattering rate, and here is the differential scattering rates between the cosmic ray and the dark matter, and rho is the density of dark matter, and m is the dark matter mass, and this one is cross sections of dark matter scattering with CR, and this is the flux of the CR. And in here we focus on the local interstellar, and yes, it is approximation. In the calculations, we need to we need to consider the form factors when the cosmic ray scattering with the dark matter, and it should be included in this scattering cross sections. So with this one, we can have the flux of the CRDM. It is very important step to, it is a very important step. So this is the flux of CRDM, and we integral in the site, and the D is the distance between the source to the observer, and then we integral over the whole space, and we parameterize the distance, the interstellar effects with the effective scattering length. Yes, and then we can, this will heavily reduce the calculations. So the second step is after the dark matter is accelerated, it will pass through the atmosphere and the Earth, and the energy will lose. And we need to consider the attenuation effects. So the key point is to calculate the flux of the CRDM when it passes through the Earth. So here, this one is the flux of the CRDM at the depths of the Earth, and this one is flux above the Earth, the flux of CRDM above the Earth. It is an initial condition, and this is the final results what we need, and they can be related by this transformation. And so the problem, the thing that we need to do is to get the energy, the dependence of the energy on the depths that the dark matter pass through. So here is this is a energy dependence, the energy of CRDM with respect to the depth of Z, and it is described by these equations. And the N here is average density of Earth's 11 most abundant elements, and this one is the CRDM scattering with nucleus in the Earth and atmosphere. And this factor, if it's isotropic interaction, this interaction can be approximate to this one. And then we can integrate out these equations. And with these equations, then we can relate the initial initial energy of CRDM and the energy of CRDM at the depth Z. So it is just normal integration. Then we can have these ones. So we can calculate these factors, and these factors you can see it is related with a parameter L. This L we call the free path, and this free path is inverse proportional to the scattering cross sections. That means if your CRDM was boosted heavily, and the interactions between them, between it and the materials in the Earth will be strongly, and it will lose energy very heavily. So, and won't reach the direct detection experiments, the location of direct detection experiments. So this is annotation effects. The last step is to calculate the direct detection rate. So this is the standard formulas to calculate it. With this rate, we can compare it with the xenon results, the constant xenon results. Although the constant direct detections for WIMP dark matter has no sensitivity in the very low mass range, sub-GeV range, but in this case, all dark matter are very energetic, and so it is boosted. So it will be equivalent very heavy dark matter. I mean the heavy compared with to the sub-GeV. So it can, so we can, this make us can use the constant direct detection results for the WIMP dark matter to look for the sub-GeV dark matters. It is something like recasting things. So with this, with those data, we can give the limits on the sub-GeV dark matters. So for our case, we consider this is the above this above discussion is model independent, is almost model independent. For our case, we will focus on the gravity mediated dark matter. This is effective interactions between the star model field with with a massive KK gravitons, and so this is dark matter interacting with star model particles, and it is here I have to mention that it is a phenomenological study. So such a we will not focus on too much of the model buildings. If you are interested in model building, you can search for or Google the warp dark sector, and in their papers, and they will discuss more about the model buildings for a sub-GeV dark matter with a gravity mediator. This is the result for the flux. So we can see, we compared the tensor case or with the scalar and the vectors. This tensor case is just what we said, the gravity mediators, because the mediator is a spin 2. So we can see the scalar and the vectors have the similar features. So in the low mass, in the low, if the dark matter energy is very low, the flux is almost the same. But for this range, you can see it can be boosted, and we can have a larger flux, and these numbers are corresponding different dark matter mass. And but the tensor is different. So you can see for the in this low energy range, for the heavier dark matter mass, it will have larger flux. This is because the interaction of the tensor interactions, it will make us the scattering cross sections is proportional to the darker mass. So that will give a very special results. So so this is the final results for the direct detections, and we can see that this is for the this is for the scalar and vector and the tensor case. So we can see that with the cast xenon 1T results for the WIMP, we can recast their results and get the font for the sub-GeV dark matter range. And this range, this shadow range, corresponds to the constant scattering cross sections, because in all calculations we include the full momentum dependency effects. So, but for this one, they keep a constant cross sections and neglect the momentum transferred effects. So we can see if we include the momentum transferring momentum effects, we will have a stronger limits than that. So it is very interesting. So that means we can use the existing direct detection data for the dark matter, for the WIMP dark matter, to study the sub-GeV dark matter. So in that case, I think we can also consider about how to use the neutrino detection experiments results to do the similar things. So I'm not sure. There is some studies in this topic, but I'm not sure whether the neutrino or the future neutrino experiments can give similar or stronger limits. I don't know. I just curious about these things. So this is our work on the CRDM, and finally, I think I can talk about our very recent works. Actually, it's not very recent. We did we did this project. We did this project. We have done this project over several months, but it is very difficult to find the feasible parameter space. So it is a KEV gravitino for solving the H0, H0, or the Hubble tension. So the Hubble tension problem is the question of the expansion rate of the universe. So in the there are two values for the H0. So one is early measurement as CMB, and this is late measurements. We can see there the measurements are different. The values are different, and the discrepancy is around above 4 sigma. It is from particle physics view, it is very large, but in the cosmology, some colleagues said it is interesting, but not as not very confirmative. So here I won't talk about too much about the experiments, and I assume both groups, those groups all their measurements are reliable. I won't talk about too much the systematic errors to explain the hypotension. I just want to start from the particle physics. So there are some solutions for these tensions. One, we can use the dark energy, and then we can also have the self-interacting neutrinos, only decaying dark matters. There are many other options for this to explain this tension. Here, yeah, the basic, the starting point to, the starting point to considering this things, this tension is Friedman equation, and in the first Friedman equations, we know there are several components, several terms. So if we assume a flight geometry, the curvature contribution can be neglected. Then we have the radiation contributions, the matter density, and also the constant. This one related with dark energy, so we won't touch this one. So we can only play the game between the radiation density and the matter densities. So there is a very interesting thing is that the matter and the radiation density have different dependence on the skew factors. One is -4, one is -3. So that's give us chance to play the game to solve the H naught tension. So the idea is like this: if a portion of dark matter density is transferred to the radiation, then whose density? We know the radiation density is diluted at a faster rate as the universe expands. So in that case, we can reduce this. If this happens, we can reduce these ratios and explain and relax the tensions of Hubble tension, Hubble constant. So we know that this is the explicit for dependence of the dark matter density on the skew factor, and this is for neutrino neutrino density on the skew factors. The neutrino is almost massless, so it is behave like the radiation, and it goes A to -4. So so there is chance that we can mimic the dark matter like the neutrinos. So at the matter radiation equality, so that means the skew factor is around 10 to -4. So if we use this value to calculate these two density, we can find that one neutrino species represent about 16% of dark matter density. In other words, if the dark matter particles has a boost of 16%, they could mimic the effects of neutrino species and increasing the Hubble rate. So this is this part is studied by Dan Hooper and other colleagues, and they found the dark matter. If the dark matter is boosted, is highly boosted, it can mimic the neutrinos, and then we can solve the Hubble tensions by using the different behavior of the skew factors. So it looks like this. If there is a heavier particles decay to the dark matter plus a photon, and then if the dark matter is highly boosted, then we can have the we can treat this dark matter as almost massless particles. It will mimic the neutrinos. So that will affect the effective neutrino, the number of neutrinos. And this one can be described by this form can be described as this form. Here F is a portion of the boosted dark matter in the portion of the boosted dark matter in the total dark matter density, and this gamma x is the chi is this gamma factor is the boosted factor when the dark matter the almost massless dark matter produced by a heavier dark matter. So, oops. So here we can see the effective neutrino number is positively correlate with the Hubble constants. So we can see that this is they did the fit with the Planck data and also the Bohr, and we can see that yes, if we can have a larger effective neutrino number, we can reach the value that needed by the present Hubble constants, and with this plot we can recast their results. We can recast these results on the F versus the lifetime of the lifetime of the NLSP. So you see, we have these formulas, and with this formula and with this plot, we can recast to the constraints on the portion of the boosted dark matter versus the time of the NLSP, the lifetime of NLSP. So if we want to explain the Hubble constants within 2 sigma range, we need our points should be should lie in this red range. So okay, this is up to now. This is all about the model independent analysis. So the whole picture is like this. We transfer, we let some heavier particles decay into dark matter, almost massless dark matter, and this dark matter will goes into will behave like radiations, and due to the larger scale factors, the faster scale factor effects, we can increasing the present Hubble value. So this is a basic idea. So up to now, all these studies are based on model independent. They didn't give any realistic models. So this motivate us to consider whether we can realize these scenarios in specific models. For example, in supersymmetry, in my lava. So we begin to consider the possibility, and we focus the gravitational dark matters, because we know the gravitational for gravitational dark matters, we can have a very natural process that's the NLSP can decay to the gravitational and also plus photon. So here we want to talk a little about the gravitinos. The gravitino, it is a gauge field of local supersymmetry transformation, and it is a spin. It is a 3/2 Majorana field, and its mass is very flexible and can range from EV to the TeV. And if we choose gauge mediation supersymmetry breaking, then the gravitino can be very light. And this is what we need. We need a very light we need a very light dark matters. And so And so it seems the gravitational dark matter is what we want, and it satisfy, roughly speaking, it satisfy our requirements. But it is not easy to satisfy all the constraints. The first one is the radial density of the gravitino. As we know, that for a very light gravitino, so we have the gravitino problems, and that means because the interactions between gravitino and stem particles are very weak. So for such light dark gravitinos, it will overclose the universe. So we need to consider how to solve these problems. And in our study, we use the dilution factors from the messengers. That means we allow the messenger to decay to stem particles, and then it will produce more entropy and dilute our radial density to get the correct ones. And also our radial density, our dark matter composed of two parts. One is the thermal production gravitino, and after the reheating, after inflation for higher reheating temperatures, part of some gravitinos can be produced in the thermal bath. Also, we have we need the non-thermal productions. So besides this one, we also have the BBN constraints, because the late decaying NLSP will inject the photon into our BBN universe, and that may affect the BBN. Then we need the lifetime of the NLSP should be not too long. And also for such a light dark matter, we have the light structure constraints from the free stream observations. And also we need only a very small portion of the dark matter come from the decay from the non-thermal productions, and a large part of them from the thermal production should be still cold. So, but it is very good. The dilution factor can help us to reduce the speed of dark matter produced in the thermal part. So, given all these constraints, we perform the scan. It is a very preliminary results. We can see that the yellow part is allowed by all the sample. Is allowed by all the constraints, and because the thermal part radial density depends on the lepton mass, so it gives a bound on the lepton mass. It cannot be very heavy. But this is very rough results, and we are refine our calculations, and there are several a couple things to check. And but anyway, it seems the lepton cannot be very heavy in our case, and and this is motive us this will this needs us to consider the LTC bonds. So for such a light leptons, it suffers strong constraints on the LTC data. With my mind, I think it cannot be less than 400 GeV. And the binary mass is very light in our case. It is constrained by the free spin line constraints. And so if we recast the LTC data, we will exclude most of this range, and we hope the highly agnostic LTC can exclude the whole range. So this is very preliminary results again, and it may different from our final results, but roughly speaking, this is what we have now. And in summary, and KeV gravitino dark matter seems good, seems a possible way to solve the Hubble tensions in particle physics. So, okay, this is all from my talk, and sorry for oh yeah, it's sorry for the longer time, and thanks for your attentions and welcome to Nanjing.
Thank you very much, Ray. We are over the time, and unfortunately I have to run to another meeting as well. So I'll go over the Mikael. Maybe he will mediate the question.
Yeah,
okay,
yeah,
okay.
happy to do that.
Yeah.
So does anyone have questions? So who wants to go first?
Yeah, can I just ask a quick question to clarify something? I was a bit confused when you showed the plots of the dark matter flux in the scalar vector and tensor case.
Yes.
Yeah. So I see that in the scalar and vector, the flux is lower for higher dark matter masses, presumably because of like the number density goes down when you have a higher dark matter mass. But in this case, it's reversed because you say there's an extra factor of the mass or something in the quantization. Is that right?
So, yes, something like that. Yeah. You mean the inverse, the difference between?
So it scales in the reverse direction for the tensor case.
Right. Because in the tensor case, we notice that the amplitude is proportional to the dark matter mass.
Yeah.
So
okay,
yeah.
But then for your limits, they all look pretty similar. So I'd expect the limits to also be reversed, like they would get better
because
for larger masses. Is it something to do with the attenuation wins out or something?
Yes. This part is they look the same because of we need to consider the attenuation effects, and also if you right, this similar behavior is, and there's another problem is for this part the flux is very slow, very small, and so in this plot it's not very obvious in this plot, and also the larger scattering cross sections will lead to a very small free path, and those parts dark matter cannot reach the direct detections.
Yeah, okay.
Yeah.
Do we have other questions?
Like, I had a couple of questions for clarification. Can you go back to, hi Lei, how are you doing?
Good.
Very, very informative talk, thank you. Can you go back to slide 16, please?
16?
Yep.
Okay.
So you're making an argument here about spin-independent versus spin-dependent access to the blind spot region. And I'm sorry, I didn't quite follow the point you were making. Can you?
Okay, yeah.
Can you make that again a little more slowly?
Yeah, sure. So sorry about the confusion. So if we calculate the spin-independent scattering cross sections, the mediator between the dark matter and the nucleus is Higgs. So these couplings is proportional to this factor if we tune the factor and the sign to cancel with the sine 2 beta, then these couplings will goes to 0. So the spin-independent interaction cross-section will goes to 0. So this corresponds to this part. But for the spin-dependent case, it is different. It is mediated by that boson. Okay, then the coupling will be changed. It will be different from here. The cancellation effects will disappear for the spin-dependent cross-section. So then you see those samples will go there, and these blind spots will disappear in the spin-dependent detections.
Okay, so let me see if I understand. There are
two different processes.
Yep, no, that part I understand. So for the spin-dependent, the green points are the green points are the values of the cross section for, you know, these sort of randomly chosen points that you've gotten over the available SUSY parameter space. Is that correct?
Yes, yes.
Okay, so can you remind me why those points disappear below about, is it 10 to the 4 in the spin-dependent cross-section? So
because we will not have this cancellation effects in the spin-dependent.
No, but okay, sorry. Like then you have two arms of this distribution. It plunges on the, as you go up in mass, it plunges as you get to around about 40, it cuts out, and then it reappears at about 42, 43.
You
remind
mean
me why?
Oh,
yeah. Why does it cut out in the middle?
Okay, because this gap from the relic density constraints.
Okay, that's the relic density constraint.
Yeah.
Okay, fine.
Okay.
Fine. All right. So there's there's a gap there from the relic density constraint, but then there's a blind spot around that which is wider that makes. Do I understand correctly? So there's a relic density constraint in the middle, a blind spot around it, and then a region where we currently see things.
Right.
So I was confused between the blind spot and the relic density constraint, because the points because the points are missing in the spin dependent the same way they are in the spin independent, and I wasn't understanding the distinction.
Okay. So, sorry for the confusion.
Okay, so now I think that's more clear. The other was when you're discussing the cosmic ray upscattered dark matter. Yep. Do I assume correctly that there'll be no modulation signature for the upscattered dark matter because it's energetic? Is that correct interpretation?
I'm not sure. I'm not sure whether we have the modular effects should be observed.
Because the argument with the annual modulation is that the dark matter is essentially at rest in the overall rest frame of the galaxy and is acting as a gas, and we move into it, and therefore we experience a wind, and that's modulated by the motion of the Earth relative to the sun. But